This is my second physics lab on the motion of a falling object. So the purpose of this lab is to compare position versus time graphs of free fall motion in the real world, which has drag, and computationally simulated free fall, with one with drag and one without. We want to understand the forces working on the object, such as gravity and drag. The results of this experiment were that the computational model with drag force is closer to the actual free fall in the real world than the one without it. The system in this experiment is the object and the surroundings is everything else. So one of the fundamental principles is Newton's second law. It relates the net interaction between the system and surroundings to the observed motion of the system. And the formula for it is F equals ma. Having unbalanced forces causes acceleration, and in this experiment, the forces acting on the object are gravitational force and drag force. These forces do not cancel, which means the net force is not zero, and this leads to acceleration of the object. And here's the velocity and position update. Gravity causes the object to accelerate towards the ground at a rate of 9.8 meters per second squared, and the drag force is there's drag force when the object is in motion in a fluid. In this case, the object is in the air. So here's my tracker video. The system is the ball, the surroundings are the air. And here's the data for it. It took a time of 0.53 seconds, and it started at 0.979 meters and ended at 0 meters. So this is my code for the computational model with gravity, but without drag force. So I set the mass to 0.2 kilograms, the position vector to 0.979 meters, and the time to 0.53 seconds, and then calculated the velocity from the velocity update formula and the position from the position update formula. And here's the results of that. Here's the one with both gravity and drag. I found the proportionality constant through trial and error, and I calculated the drag force using this formula, which you can see here. And here's the results of that. The drag force opposes gravity, making the ball gain velocity at a slower rate. So here's the results of all of the actual, which is the blue line, the model without drag, which is the red line, and the model with drag, which is the yellow. So the model with drag is closer than the model without drag to the real life velocity and position. So possible errors in this experiment were tracking it wrong and tracker by placing the center of mass wrong. So the discussion question is, which velocity versus time models predict a terminal velocity? So here's the one without drag, and here's the one with drag. The one without drag, the no terminal velocity is reached, and the one with drag, terminal velocity is reached. This is because the velocity approaches a constant right here. The net force is approaching zero, where drag and gravity would cancel each other out. And what if the object was thrown downward? I changed the velocity vector on the glow script model with both drag and gravity to have a y component of -1. And the terminal velocity would be the same because it only depends on the drag force being equal to the gravitational force, not the initial velocity. And that's it.